In this video, we will talk about rotational kinematics, which refers to rotational motions with constant angular acceleration. We will introduce and explain equations of rotational kinematics and use them to solve problems on rotational kinematics to illustrate concepts presented. As we mentioned earlier, rotational kinematics refers to a group of rotational motion with constant angular acceleration. Let us first briefly review the concept of angular acceleration for a rotational motion. Let's assume you have a system as shown in this diagram. It could be a single object rotating about this axis that is known as the axis of rotation. This system could consist of just a single particle rotating in such a manner, or it could just be a point on the rim of, let's say, a disk that is spinning in that direction about that axis. As we explained in our previous video, because the sense of rotation is like that, the angular velocity will point in the same direction as the direction of the axis of rotation, namely this blue arrow right there. Now what about the angular acceleration vector, alpha? In what direction does this vector point? Now if angular velocity increases with respect to time, namely if this disk or the object that is spinning is speeding up, then the direction of alpha will also follow the direction of angular velocity, namely it will point along the axis of rotation. If, however, the angular velocity is decreasing with respect to time, or the rotation is slowing down, then the direction of angular acceleration will be opposite to that of angular velocity, namely it will point opposite to that of this axis of rotation. Next, we will look at the implications when the angular acceleration vector is a constant. So let's assume you have an object shown here that is rotating counterclockwise about the z-axis. So in this case, the z-axis is an axis that's coming out of the plane of that screen, and it's rotating with constant angular acceleration. Also, at t equals to 0 seconds, its angular position is theta naught, and then it starts to move counterclockwise as shown. Since we know alpha is defined as time derivative of angular velocity, we can write down angular velocity as an integral of angular acceleration with respect to time. Now, because alpha is a constant, you can take that alpha out of the integral sign, leaving you the following equation. Alpha integration with respect to time is t plus the value of angular velocity at time t equals to 0. So this is the first equation of rotational kinematics. It simply relates the angular velocity here to angular velocity at t equals to 0 through the constant angular acceleration and the time interval between these 2 points. Sometimes we can also write as angular velocity final equals alpha t plus angular velocity initial, in the case of which t is the time it takes for the system's angular velocity to change from omega I to omega f. What about theta? How does theta changes with respect to time? Now we know d theta dt is omega t. So theta as a function of time equals an integral of omega t with respect to time. Substituting this result inside here and integrating, we will get the following, which is just half alpha t squared plus the initial angular velocity t plus the value of the angular position at t equals to 0. Rearranging, we get the following term, where the left-hand side is quite simply the angular displacement of the system for that time interval from t equals to 0 to t seconds. So this is the second equation of rotational kinematics. The third equation can be obtained by eliminating the time from the first equation and substituting it in the second equation, and that's going to give you the third equation of rotational kinematics. 2 alpha angular displacement equals the square of the final angular velocity minus the square of the initial angular velocity. The fourth equation of rotational kinematics that are consistent with the other three is the following. The angular displacement is given by the final angular velocity plus the initial angular velocity over 2 times t. So that is the fourth equation. So these four equations should enable us to solve problems associated with rotational kinematics, as we shall see next. Problem 1. A wheel turns with constant angular acceleration of 0.5 radian per second squared. How much time does it take to reach an angular velocity of 8 radian per second, assuming that it starts from rest? And part B, how many revolutions does this wheel turn during this time interval? Let's first list out all the information given. We know the constant angular acceleration, 0.5 radian per second squared. We also know the final angular velocity, that is 8 radian per second. It starts from rest, so the initial angular velocity is 0 radian per second. So we can determine the time it takes for the wheel to turn from 0 radian per second to 8 radian per second using the first equation of kinematics, which is given by omega f equals omega I plus alpha t. Omega f is 8, omega I is 0, alpha is 0.5, and t is what you want to find. So then you can solve for the time interval being 8 over 0.5, which is 16 seconds. So that is the amount of time taken for the wheel to turn from 0 radian per second to 8 radian per second. Now part B, how many revolutions? Now note that we are asking here to determine the angular displacement. Now first we have to get the angular displacement in radians and then convert it to revolutions. It is given by the following. The second equation of kinematics, half alpha t squared plus omega I t. So since omega I is 0, that term goes away. It's going to give you half, alpha is 0.5, t squared is t is 16, so 16 squared, which is 64 radians. Now we know that 1 revolution equals 2 pi radian, that is the conversion. So if it's 64 radians, how many revolutions is that? It is quite simply 64 divided by 2 pi, which comes to about 10.2 revolutions. So this is the answer for part B, and that solves the problem. Problem 2. If a flywheel whose angular acceleration is constant and is equal to 2.4 radian per second squared rotates through an angle of 100 radians in 4 seconds, calculate the angular velocity of the wheel at the beginning of that 4 seconds interval. So the information we have is, we know alpha is 2.4 radian per second squared. We know the angular displacement is 100 radians. The time interval is 4 seconds, and we are interested in determining the initial angular velocity. So of course, based on the information given, the second equation of rotational kinematics would work. That is, the angular displacement equals half alpha t squared plus omega I t. So the angular displacement is 100, alpha is 2.4, t is 4, so 4 squared. Omega is what we want to determine, the initial angular velocity, and t is again 4, and you can solve for omega I, which will give us 20.2 radiant per second. And that's also problem. Problem 3. A disk turned through 40 revolutions, as it slows down from an angular speed of 2 radian per second to a stop. Assuming a constant angular acceleration, find its angular acceleration and the time it takes to come to a complete stop. Note that this disk is slowing down, so you should anticipate a negative answer for angular acceleration. So let's list all the information given. The angular displacement is 40 rev. In radians, it is just 40 times 2 pi radiant, which is 251.3 radians. Now we also know the initial angular velocity is 2 radian per second. The final angular velocity is 0 because the disk will stop at some point. Alpha we don't know. The time it takes to do this we don't know. Of course, we can get the alpha first from the third equation of rotational kinematics, which is 2 alpha delta theta equals the final angular speed squared minus the initial angular speed squared. So 2 alpha theta is 251.3 radians. Omega f is 0. Omega I is 2, so 2 squared. And you can solve for that constant angular acceleration, which will be minus 7.96 times 10 to the power minus 3 radiant per second squared. Note the negative answer as we have anticipated earlier. So that's the answer for part A. The time it takes to come to a complete stop. Now this can be determined from using the first equation of rotational kinematics, omega f minus omega I equals alpha t. Omega f is 0, omega I is 2, alpha is minus 7.96 times 10 to the power minus 3, and you can get the time it takes to come to a complete stop. And when you solve, you'll get 251.2 seconds. And that's also a problem. Thanks for watching.